Okay, so this question reads, if Q is equal to 25 microcoulombs and little q is equal to 10 microcoulombs, and the angle between the equal sides is 90 degrees, and L is equal to 40 centimeters, what is the magnitude of the electrostatic force on little q? Let's just have a look at this image. Here we have L, and we have L on both sides. They're the same length, 40 centimeters. The only difference between the two sides is that this one is negative and this one is positive. So let's just see what this means for the electrostatic force way up here on little q. So we have our charge q up here. And now, if you remember, opposites attract, so this is negative and this is positive, meaning little q is going to be pulled towards negative q down here. But over here, we have positive q. Positive and positive, it's going to repel it. So q is going to be repelled, and it's going to be going upwards. It's going to be following this line up like so. Let's call this force 1, and this is force 2. To find our final electrostatic force on Q, we are going to have to figure out what both of these charges added together are. So if we were to actually look at this right now, we see that this force 1 has two components. It has a component in the negative I hat direction, so this way, and it has a component in the positive j hat direction. Now we see negative q has one component, again, the negative I hat direction, it's down here, and it has a component in the negative j hat direction. Because we know that these two forces are going to have the same magnitude, we actually already know that the negative j hat and the positive j hat are going to cancel out, and all we're going to be left with is one force going in the negative I hat direction. But we're going to write this all out mathematically, so it's easier to see that way. Now, the equation for the force, the electrostatic force, is equal to K, Coulomb's constant, Q1 times Q2 over R squared. Let's calculate force of 1. So force 1 is this one. It's being caused by the positive Q down here. So we have K, which is Coulomb's constant, times 25 microcoulombs, which is this charge down here. It's this charge, multiplied by the charge it's affecting, so this little q, times 10 microcoulombs, divided by L squared, because that's our length, which we know from up here is 40 centimeters. 40 centimeters in meters is 0.4 squared. So if we were to do this, we know that K, Coulomb's constant, is approximately 9 times 10 to the 9 Newton meters squared over coulombs squared. And we're going to multiply this by 25. Microcoulombs into coulombs is times 10 to the minus 6. Then we're going to multiply this by 10 times 10 to the minus 6. And we're going to divide it all by 0.4 squared. You can do this on your calculator too, because I am in no way going to be doing this in my head. So the answer that I just got on my calculator is 14.0625 newtons. The reason I know it's in newtons is because I have my meter squared that cancel it with these meter squares, because we measure this in meters, and I have my coulomb squared that cancel it with coulomb squared here, because coulombs times coulombs, and all I'm left with is newtons. So I know that my force 1 is 14.0625 newtons. I'll write that up here. Now remember, there are two components to this, because this 14.0625 is this force. I need to find the components of it. But luckily for me, I know what my angle is, because I know that the angle between these two is 90 degrees, meaning the angle here is 45 degrees, because 90 divided by 2 is 45. So I have two components to this. I have cosine of 45, which is going to give me my I hat direction, and I have sine 45. For this one is going to be in my positive j hat direction. So I'm going to do my force. Force 1 multiplied by cos 45 plus sine 45. I am also having my force 2, which is affecting this. And this is going to be cos 45. Sorry, this should be negative I hat direction because we're going negative I hat. And we're going to go up in the j hat. And now here I also am going into the negative I hat direction. But I'm going into the negative j hat direction with my force 2 as well, because see here, force 2 is going down here. So minus sine 45 j hat, or I can do sine 45 negative j hat, same thing. So instead of doing the whole equation here, I'm just going to cancel out my sine 45s because I know that they are going to counter each other. And I also know that the answer I get for this is going to be the same as I get for this one because they have the same magnitude. So I'm just simplifying my life here. And I'm finding that my final force is going to be equal to 14.0625 newtons times the cosine of 45 multiplied by 2. So all this multiplied by 2. And my answer is 19.89 newtons. And that is it. But remember, it is in the negative I hat direction.